as soon as I get the slideshow set up here from current slide, this is from the next section, but I'm going to write the stuff on this one. Let's go over how things are looking from now till the end of the term. Normally on Tuesday and Thursday I have office hours 10 to 12 and 3:30 to 5:15. And a lot of Tuesdays and Thursdays up till now I've been able to stay past 5:15, but some I couldn't. Next Tuesday I have a doctor's appointment. I think I told you early in the term. My hematologist only sees patients on Tuesday mornings. That's the only time he sees them. I can't schedule any other time. So that's wiping out my differential equation class next Tuesday. So I talked with them yesterday, and we decided I would make up basically an hour yesterday and an hour tomorrow. And that will make up for the 2-hour, 50-minute class on Tuesday. So tomorrow my office hours are not 10 till 12, but 11 till 12, because I will be up here teaching that extra hour of class tomorrow. But then it'll be 3:30 until 5:15. But it looks like pretty much for the rest of the term, I've got to leave at 5:15 because I've been volunteered to do something, and they want us at a place at 5 o'clock every Tuesday and Thursday. Said I can't do it. I don't get off work until 5:15, so I have to leave here and go back to Birmingham. But it's volunteers, so they can't say too much. So I will have to leave right at 5:15 just about every day. Okay. I do know there's one other interruption for classes, and I think it's a Tuesday or a Thursday, so it won't affect this class any, except possibly at my office hours, but I can't remember what day it is. It's either a Tuesday or Thursday. I don't remember what time, but it will. It's a meeting we have to go to on the Birmingham campus, and it will mess up. I think it's my early morning class, but I'll get you that information later. But other than that, we've got class this week, next week, and I think one more week and then finals. I believe that's right. So this week is 1 day. Next week is 2 days. And I think we have 2 days of class, 1 or 2 days that next week, and then finals. Okay. Jasmine? Yeah. All right. Okay. That's all the announcements I can think of. It seems like there's one thing I was meaning to say, but I can't recall what it is. I talked with the others before they came in. I guess you showed up Monday and I wasn't here. I could not believe that the dean sent the email Sunday morning that we're having interviews on Monday. I mean, I was lucky just to see the email, because I usually don't check them Sunday afternoons necessarily. I do if I have time, but it was just, I was going to be getting something else done, and I saw that, and then I had to spend the rest of the time I was planning to do something else, sending messages to my 3 classes. And I told her I have 4 classes on Mondays and Wednesdays, please don't schedule them, so she scheduled them. But she wanted to go on vacation yesterday, so that was more important than class. Just like the vice president needed to go to a wedding in New Orleans, so he got the school to pay for it by having our meetings in New Orleans rather than Atlanta on a Friday, Saturday, which wouldn't have affected class at all. But if you're an administrator, there are other priorities. Never mind. Never. I'm recording this. Okay. So we're doing the preliminary questions for 7.6. Okay. I'm having trouble reading. For each of the following, find the formula on the integral table at the back of the book that can be applied to the integral. Okay. Let me get my pen set up correctly. Here's number 8. The integral of 3x squared dx over 5x plus 2. Okay? Now, frankly, I'm not sure I would use an integral table, but they said find it, so ask you to do any of you have books? None. Well, then what's the point of this? I can find them for you, you know, that would be really helpful, wouldn't it? But you can find integral tables, and I'll just give you a little bit of a hint. It's in a grouping that says forms involving a plus bu. That's exactly what you got in your denominator there. And there is one there, and it happens to be, I think, 93. If you have a book at home and are following this, I'm in the wrong section. 7.6 preliminary questions. Oh, number 8. Well, they said here, find the formula in integral table. They actually showed what it is. Number 9. Is the integral of the square root of 25 plus 16 x squared over x squared dx. Okay? Now, that would not be the same type, but it's one somewhat similar, except it's integrals involving the square root of a squared plus u squared. You would have to adjust that numerator to get it into that form. The bizarre thing is it does have something in the denominator, and it happens to be that integral number 87 in the back is the one that matches that. Okay, number 10. And if you have other tables, of course they won't go by this number, but you know, whatever. Here's one that's the integral of secant cubed of 4x dx. Now, of course, that will have a little substitution to do for the 4x, but other than that, secant cubed, those would be integrals that are trigonometric forms, and the secant cubed is number 42, with this substitution that you would have to make it work. And then number 11 would be the integral of x squared over the square root of x squared plus 2x plus 5, and that would be a dx. Okay. Now, I doubt if you'll find one that looks like that in an integral table. Okay? So what would you do? Any guesses? Yeah, there's nothing in the integral table in our back of the book that looks like that. What would be your first move? Kind of a little trick, but it's not that tricky. It's something you do fairly regularly, not super often. Say again? Okay, you mean write it as exponential notation? Okay. Now, there could be a little bit of promise in that, but it's not much, because even then, the x squared plus 2x plus 5 is not factorable, so that's still not going to be helpful. What you do in this is, in that radical, as it is, complete the square of that trinomial and make it something squared plus or minus something else. That something squared would be at x plus 1. Guarantee that's going to be the x plus 1 squared plus something else. The x plus 1, a little substitution there will work, and then you have a form that would be the square root of a squared plus u squared, or u squared plus a squared. It doesn't really matter, but that would be something of the form of it would be forms involving that, and you would just have to see what it pans out to be. Frankly, I don't see one that's exactly like that, but that would be the direction to head. Oh, there it is. There it is. Number 89 in the back. Okay, that would be the one that would then look more like that. Again, there's a little substitution you have to play around with to get it to work, but that would be what you would do. So there are some tricks to do, but that's what you would do. All right, now that finishes 7.6. Okay, 7.7, you're not. I've got to check. I think it's here. I don't believe I did any infinite integrals on your test. We basically lost 2 weeks of class. I'm sorry about that. Memorial Day was a Monday. Then when the Vice President changed the meeting from a Friday, Saturday to a Monday, Tuesday, that lost us a day. Then when the governor gave us the Monday before the 4th off, that lost us a day. And then yesterday, or Monday, when the dean decided to have interviews on a Monday, that lost us a day. So basically, a 10-week term became 8 weeks. So I left off this part. I will go over it quickly, just a slideshow, if I can do anything quickly. That's not what I wanted. Okay. Let me erase. Well, there we go. Erase this ink. Now, in a lot of applications, in some areas, way more than you might realize, you're actually dealing with areas on the curves, but sometimes these curves are infinite curves. Anyone know what that is? Your bell curve, okay, which most students love and dream about, and hope they pass on the bell curve, okay? This is where it comes from. And basically, what your 1s and 2s and things are basically what they call standard deviations. Okay? And basically, if you really were graded on a bell curve, anything less than 2 standard deviations this way would be an F, D's, C's, B's, and A's. And really, most students don't want to be on the bell curve because that's so few A's. Okay? You really want to have a little bit better grades than that. Okay? But that is that, the integral of e to the minus x squared over 2 dx. Any of you think you can solve that? Good luck with that, okay? It really isn't something that's really all that solvable. But it's so standard, we have all the data for it, and anything in statistics is going to use something similar to that, okay? That's why statistics is not a very precise science, because you're based on something that's really, you can't measure anyway, but you can come real close. So that's an example of an infinite integral. There is no end to that. E to the thing that goes on forever. You can plug any value, negative or positive value of x in there, and you can still get an answer somewhere. But it's going to zero so quickly there, it never gets to zero, but so quickly you can deal with it because it's, and we'll talk about that. That's an example of an improper integral, okay? There are two ways that integrals can be improper. The interval of integration, like here, is infinite, or the integrand may tend to infinity. So we're going to look at these separately. This is the one where the interval actually, that goes from minus infinity to positive infinity. That function never touches the x-axis, okay, at all. Okay? So here is an example of one that's given in the book on page 414. And again, you don't have to, we're not going to really do anything with them, but I just wanted to let you see what they are and how you go about doing it. If we were doing e to the minus x from 0 to infinity, well, that has a starting point, and it starts at 1. When x is equal to 0, this value is 1, and it approaches 0 as you go, but never gets there. If you were doing that, then what you do, the technique, the trick, is take the limit as some capital R, that has nothing to do with radius, it's just a letter they use. That R is approaching infinity, and do this integral. Well, that's an integral you can do. You can calculate that integral. That has a thing, and this is a finite number. It's just a number approaching 0. Well, then when you find that integral, that's what the integral is. Then you let R approach 0. This thing goes to 0. That integral is going to be 0. Okay? The area under that curve, that portion of the exponential decay curve from 0 to infinity is going to be 1. Okay? So that's how you approach it. If one of your, the first case, if your interval of the integral, one or the other, or both of them, is going to infinity. Okay? So that's the technique. Okay. Now, here is a little bit of an illustration of what was happening with that very problem. I can't get them all on here, so let me just do the first two first. Okay? This is a finite region where you have that R there, and you can actually calculate the area 0 to R of this thing. That's what we did. Okay? But then if you let R get larger and larger, then that area, if you look at that area, is getting closer and closer to 1, so that even though the interval here is unbounded region. In other words, it keeps going because that never reaches 0, so it keeps going forever, but still that region is getting closer and closer to 1. Never quite reaches 1 itself, but the limit for it is x goes to infinity would be 1. So that's the pictorial example of what we just did. So here's your definition then. If you ever have to do these things, here's the technique. For the first type of improper integrals where the interval is approaching infinity, okay? Fix a number a and assume that f of x is integrable over some interval a to b, okay, for all b greater than a. Then the improper integral of f of x from a to infinity would be defined as the following if the limit exists. Now, if the limit doesn't exist, you're out of luck, okay? But if the limit does exist, you do it. The integral from a to infinity of f of x dx, of course, f of x has to be an integrable function. And if it is an integrable function, and you set that the infinity to some value r, and then take the limit and let that r approach infinity. If you can integrate this integral for some finite value r, then whatever that comes out being, see if the limit of that function r approaching infinity goes. If that r turns out being a polynomial, hang it up. Polynomials will never be, if r is getting large, the polynomial is getting large. It's only if that r is in a denominator to some extent that it does have a limit. But not even that will guarantee it. We say that the improper integral converges if the limit exists and is finite, and that it diverges if the limit does not exist. So if that limit here as r approaches infinity of this, even though this is an integrable function. But if the limit of that function as r goes to infinity is blowing up, then it diverges and the limit does not exist. However, if the limit does exist as r goes to infinity, then the function, this has a an answer, it has a value. Okay. I can't even read what those are. Let's see, zooming in will help some. Okay. Now, what if we had infinities on both sides? Negative infinity to the left and positive infinity to the right. Then what you do is break this integral down into minus infinity to 0 of that function. Add it to 0 to infinity. That's going to give you the same thing. Then do a limit of this one as r as make this a minus r, and if that has is integrable and it has a limit as r approaches infinity, then that might work. And you do the same thing here. Put this to r, then take the limit as r goes to infinity. If both of them work, then you have it. If one of them works and one doesn't, you have no limit. If neither works, you have no limit. Okay, so that's the same technique. You just break it into two pieces and then do two limits. Okay? Now, this is example 1. Okay? We're not going to do it, but it says show that the integral from 2 to infinity dx over x cubed does converge and compute its value. Okay? Well, of course, the technique then is to set some r down here and do 2 to r, and then this certainly is something you can do. I wouldn't write it 1 over x cubed. I would write it as x to the minus 3. Integrate that 2 to r, and then let r goes to infinity, and you'll find that does have a limit. Okay? And it's a d equal to 1/8. You don't need to know that, but if you did the work, you would know it. Okay? This, on the other hand, and it's not because it's starting at negative infinity, it just happens to be it's a different kind of problem. This is an integral from minus infinity to minus 1. Okay? But it's f of x is 1 over x, or written better, x to the minus 1. Okay, now it looks like that's going to 0 pretty fast here. So you might guess that's going to a limit. It doesn't. Okay? Because if you were to do this, what is the integral of 1 over x? See, this is the one I wouldn't write as x to the minus 1. The natural law. And yeah, you don't even want to mess with natural laws with negative numbers, but not going to work. Okay, so that one will not. That one would be infinite. Okay. Now that leads to theorem 1, which is top of page 416. And this is a very handy dandy tool that you use, and looking at it you might think it's not a very useful tool, but it really is. It's called the p integral over a to positive infinity. Okay? And as you saw before, if that p was 3, it had a limit. On the other hand, on the other side, if that p was 1, on the other side it didn't have a limit, and I think you'll see the reason. What the limit is, if p is greater than 1, in other words, 2, 3, 4, even 1.1, 1.01, 1.0001, any p greater than 1, then this will have a limit, and that will be the limit. That integral does converge. If p is equal to 1 or less than 1, this will not work. Of course, if p is less than 1, let's say 1/2, that certainly wouldn't work. But if it was even a -1, then that would be a polynomial, and that wouldn't work for sure. Okay, so any p less than 1 or less, this form will never, ever, ever converge. If it's greater than p is greater than 1, yes, it will. No matter how much little greater than 1, as long as it's some value greater than 1. Because look, p equal 1, that would blow up anyway. Okay, but p anything greater than 1, that would have the value 1.0001. That would be maybe a 10,000 down here, but it still wouldn't have the value. Okay. 1 over, let's see, 10,000th down there, which would be a 10,000 up there. A big number, but it would still have a limit. Okay. Now, this is an example now of we haven't gotten to example 2a, or the book had. This is one of those limits that if you're going from here to infinity, that would not have a limit, because that your p would be, this is 1 over x to the 1/2, the 1/2 is less than 1. And as you see, that's going to take a long time to go to 0. It's never going to have a limit. The weird thing is, it does have a limit going this way, even though it seems to be going to infinity up there. I mean, that's a huge number going up there, but this does have a limit, okay? From 0 to 1, okay? Of course, it can't be 0. That x can never be 0, but from as x approaches 0, that will have a limit. Okay, so we'll do something else with that p rule, okay? In fact, here it comes, I think, right now. Now, this is your general, this is just definition. This now is your integrands with infinite discontinuities, not with an infinite interval, but with an infinite discontinuity, like we just saw. If f of x is continuous from a to b, counting a, but open-ended at b, okay? But it's continuous at x equals b. It has no limit. It's this kind of continuous function at x equals b, but it's approaching b. Then if you do this integration from a to b of f of x dx, now of course, we assume that f is integrable. If it is, then a is not your problem. A is fine. It's the b is where it's discontinuous at b. Now it never reaches b. It's approaching b, but never reaching it. Then when you take the limit as b, r approaches b from the minus side, from the downhill side, if that limit does exist, somewhere if f is continuous on a to b, but discontinuous at x equals a, then your discontinuity is on this side. That's like your 0 was before. Then you just let that be your limit and evaluate this at some fixed value, just like we did before, and then take the limit as r approaches that a from the plus side. If that limit exists, then you have it. In both cases, we say the improper integral converges if that limit does exist, and it diverges if it doesn't exist. Okay? So we'll get to another example of that in a minute. Here we go. Thought it was going to be a little longer. Here is that the next p test, or p integral, they call it. This time, the p integral over an interval from 0 to a. So you're going from 0 to a. And really, that I think should be an open parentheses there, because x can't be 0. Okay, but if it's going towards 0, so I think that should be really an open there. Your dx over x to p. This time it works if p, it doesn't, okay, I'm sorry. It does work if P is less than 1, okay? And it doesn't work if P is greater than or equal to 1, okay? And this would be your answer there. And of course, pretty obviously it can't be 1. So there is. So if you ever need to do any of these, basically, these are the forms that you would go to do. But if this P is remember before when this was your limit going to infinity, if that P was a large number, it would work. Now, if it's a large number, it's not going to work, and if it's a small number, it will work because you're going from here to there. And it was sort of like that square root function. It closes really closely there, but stays open a lot longer and as you're going to infinity. And here's Chris. Has anyone else come in since we called roll? Okay. Now, here is kind of a pictorial representation of what we were just talking about. Okay? When your upper limit, when your interval is going to infinity, in other words, as the interval is going to infinity, then you want this P to be a big number. Okay? Like that. That would have a limit coming this way. Okay? If P is a small number, okay, yeah, both of these work. Okay, if P is a large number, this has a limit, but this one would not. Okay? If P was greater than 1, this wouldn't have a limit. Like, do the pink curve here. That doesn't have a limit, that does. If P is less than 1, I'm sorry, Q, in this case, less than 1, then this one will have a limit, but this one will not. See, this closes up pretty quickly. Doesn't ever quite close, but it will have a limit. This one doesn't, and so it won't. Going the other way, like I said, if the Q is small, that will have a limit. Q is a small number, and you're going this way, yeah, it's not going to close enough. The P will here, if P is large, nothing will go there. Okay. So that shows the differences in the two tests. Okay. All right. Now, here's another infinite limit, and the integral is going to infinity, not the interval is going to infinity, and that sure looks like it's going there pretty quickly, and so therefore that will have a limit. Now let's see. Your x then is always less than 1, going to infinity, so that should be okay. And this shows that the PQ test again, pretty much similar to what we had before. Oh, this is exponential now. What this is showing is basically the comparison thing. If you have a function you know has a limit, and you have another function that is always, the area under there is always less than or equal to that, then that has to have a limit too. So that's a comparison test. So if one of the others, if you come up with the P test that works for you, and you can show that's always less than the P, then that would work as well. Okay? So these are your comparison tests. And you can use these as well. And again, I'm not going to test you on these, but if you ever do need them, at least you'll know where to go back and look for your answers. Assume that f of x is always, always, always greater than or equal to g of x, but they're both always positive. They never are less than 0. So f is greater, g is in between, 0 is the minimum. For all x's past some value a, okay? Then if this integral from a to infinity of f of x dx converges, and it's the bigger function, then you know the g's got to converge because g's always less than the f, okay? Now, if g diverges, then certainly a bigger function's got to diverge as well, okay? The comparison test is also valid for improper integrals with infinite discontinuities at the endpoint. So you can do the same thing there as well. Okay. Now, if the bigger integral here diverges, and this one you know is less than it, you can't guarantee that diverges too. I'll look at that when I say, sure, it looks like it's got to, but you don't have anything. Now, if you could show this one that it did converge, having a bigger one, you can't say anything about that either. So you would have to use a comparison test. You're comparing, the thing you're comparing has to converge and always be greater than this one. That one diverges even though it's greater than that one, but there's nothing you can say about it, though it does certainly look like it would work. So here's sort of a summary of those rules for the p's and the q's. P's, I guess it is. If p is greater than 1, then the integral with a large exponent here going to infinity, x going to infinity, that will definitely converge. Okay? But if it's going 0 to a, and this is going to, that's your problem at 0, not at a. If the p is large, then this is going to diverge. If your p is small, meaning less than 1, this always diverges because that's going to be a small number here, which makes a bigger number when you flip it over. So that would diverge, but going from 0 to a, that was going to converge. If p is equal to 1, everything always diverges. So if that p is equal to 1, x here, that equals 1, no matter what your intervals are, that's not, both of those diverge. That was all we were going to do about this. And again, I hope you're not going to need it that badly. If you do, go back and check, okay? But that's, we just don't have enough time. Now this next section is similar. In fact, it's talking about exactly the same thing. Well, not exactly the same thing, but it's very similar to our first example. And the bell curve is used a lot in probability. Anything dealing with probability. Have y'all had any stats for probability? You have. You what?
How they teach them stats.
Okay. I don't know if you realize that what you're dealing with is area under curves. When I was doing my graduate work at Nebraska, they required us to take what they called biostats. And so it was mostly agricultural type people. They kept the math as simple as they could do it. And then they just had rules and rules and rules, you know. And it was frustrating until the second term that I took it. That lady who was the professor for that one, she didn't pull any punches. She drew curves on the board and said, this is what you're measuring. I said, why didn't they say so? As soon as they got a curve up there, because I had calculus and it made perfect sense, that's what you're dealing with. But when you just try to do statistics from just a rule basis, it can be extraordinarily frustrating. So basically, statistics comes from calculus, really. And it's kind of, I don't know if y'all have this feeling about physics or not, it's almost a shame to try to teach physics to someone who hasn't had calculus yet, because most of physics is based on calculus. Otherwise, you just have to memorize formulas and try to remember why those formulas work. Well, you don't know why they work, but if you know their integrals and derivatives and stuff, oh, of course, yeah, that makes sense. Okay, statistics probably even worse. Okay, when you're talking about probability, if you have a distribution, and generally with a distribution, the probability of being in that distribution is always 1. I mean, I guess you could have things, but if that's always 1. So everything is normalized, so the area under the curve is 1. And then you look at the probability of being between 90 and 100 or yeah. Now this is often how your curves look. They're not bell curves, they're curves. Because usually we give probably a larger number of A's and fewer numbers of F's. Okay. At least.
Boltzmann distribution.
What's that?
Boltzmann distribution.
I can't hear you.
Is that a Boltzmann distribution?
It could be, yeah. They haven't named it, but yeah, that could be a Boltzmann. There are also some of the others, Poisson's distribution. There's several. This probably is more like a Boltzmann. Again, that's not my favorite area, so I don't deal with it. But generally, your distributions are, and notice they didn't label this. They labeled this. All your grades are between 0 and 100, okay? So the probability of getting one of those grades is 1. So they didn't say what this scale is, but you know the total area under the curve is 1, because you can't get anything outside, and everybody in there is going to be. So from 90 to 100, this would be 15%. 15% of the class would be getting A's, basically, is what that would be saying. If that were your distribution. Because I don't think they did this. They just called it a probability density function. Okay? Now, this is what I was just saying, written in math speak. The integral from minus infinity to infinity of p of x is going to be 1. Wherever your limits are, the one I showed, all the scores are between 0 and 100, so they were finite. So the probability of being one of those scores is 1. Okay. If it was an infinite function, for instance, like your e to the minus x squared over 2, those kinds of things, then generally you want your probability of being somewhere in there to be 1. You can't have any more than that. So that's generally true in probability. Okay. And this is just some other probability density function. I'm not sure it has any specific value or meaning to anything, but it just happens to have some, it just shows some value for it. And if you were to do this one, integrate that, if you could, I'm not even sure you could, but if you could, the integral of that is supposed to be 1. The whole thing going from minus infinity to positive infinity. Now, in reality, you probably don't live out there at the infinities anyway, and they're getting progressively less likely out here. So I don't want to call these standard deviations anymore, but they're somewhat similar to that for this function. And you see most of your things are plus or minus 1 of those. A fair number added there, and then even more with getting less and less every sort of like a standard deviation you go out. After a while, you're not making much change to the whole thing anyway. I think in the normal curve, I'm trying to remember, after 3 standard deviations, you're 0.99 something another. You're basically almost it all.
97.
97? Is that 3? Okay. 4 would be 0.99 something. I mean, it goes to 0 pretty quickly. I mean, not to 0, but it becomes decreasingly important for each standard deviation further out. Okay. Now, one thing that we deal with a lot in probability are means. And basically, usually your capital X stands for your expected value. I don't know if that's what they're doing in this. And so this would be your mean expected. It would be your X times the probability of that X, the integral. And that's how you would find what your anticipated true mean would typically be. So that's just another formula, and this is what sort of drives me crazy about probability and statistics. They just throw a lot of formulas out there without giving a huge amount of rationale of why it's true. But really, it's a, think of it as a weighted average type thing. Whatever your value is times the probability of that value. That's basically what you're getting to. Now, this is one that's real nice to work with. I am not going to say that it shows up all that frequently. You wish it did, but this is a good old exponential probability. And this is very regular in its pattern, and it's called the exponential probability density function. Okay? And again, just sort of exposing you to this, but I'm not going to test you over it. Another thing that you will run into, this isn't quite the same thing. This is, people have done studies on it and found out that customer arrivals have an exponential distribution. They're not saying what these numbers are actually representing, but where this type of thing has, to me, the greatest application is when you're talking about confidence intervals. If you're within this band, you have a confidence of, certain things show, and they do use those in research and statistics quite a bit. Confidence intervals. If you're between these two, you have a fairly reasonable confidence that you're going to have, meet these criteria. So that's used a lot. My wife's an epidemiologist at UAB. She studies diseases, and they deal with confidence intervals all the time. And that's maybe a stretch on an application of this, but it is an application of that. Now, this is, I'm pretty sure that is your normal distribution. Yeah, that's your normal distribution, normal density function. Okay, that is your true bell curve. Okay, and you might wonder where in the world does that 1 over root 2 pi come from? It's just there. That's your normalizing factor that guarantees this thing is going to come within, have a total density of 1. Integrate from minus infinity to infinity. Now, what do we do with that? Okay. This now, with a few more things thrown in here, notice that your 1 over root 2 pi is still there. Your e to the minus type thing is here, but now they've thrown in a sigma, and sigma stands for standard deviation. So you can have a variety of standard deviations, real thin, real thick, or whatever. Your mean here is your mu, okay? Most of the examples we've been looking at, the mu has been 0. You're assuming everything, but you see your mean can be out here somewhere. It could be anywhere. So that's why that factor is there. That's a horizontal shift that sets your mean wherever it happens to be. Now, here is a pictorial representation of how some of these changes can happen. Okay? If your mean is 0, then that means your curves don't peak at 0. Okay? The mean is 0. This has a standard deviation of 0.5, meaning that you're going to have that. See, if this is about 1, that would be 0.5. That's where, what is it, 68%, something like that, of your values are going to be within that standard deviation. Okay? Within 0.5. This is your normal one. That would be when the standard deviation is 1. Standard deviation is 2. Then you spread out. So that means that you, between these two, you have, is it 68%? Seems like that's about right.
Rule is 68.
It's what?
54, 68, and then some in.
Yeah, something like that. Yeah. So anyway, that's what they are. And you see the smaller your standard deviation, the more precise, basically, you're getting in your data. The larger your standard deviation, you got smears all over the place. Think of it. Do any of you do any target shooting or anything like that? Okay. If you do, if this is the target here, okay, and your shots are all over the place, but they're averaging 0, that could be, on average, you're pretty close to the right, but your standard deviations are all over the place. Now, if you group all your shots right here, that means you're precise, you're just not very accurate. That means you have a calibration problem. Your sight on your gun is off. You need to fix that. That would be something like this. You have a pretty good precision here, but you're way off from what, or maybe that is the mean that you wanted to have. This is with your mu somewhere other than 0. Mu equals 3, then you're centered at 3, and your standard deviation is between 0.5 and 1, so you're in between those two curves. So those are how normal distribution density functions can vary like crazy. Okay? And perhaps we wouldn't mind if this was our great distribution, that everywhere in there were C's, B's, and A's. It still comes out probably not as good as what you would want it to be. So most of the time, you really don't want that. Now, here is the actual integral that you're doing for your standard normal cumulative distribution function. Okay? Quite a mouthful there. Okay? And again, that's very similar to what we had before. This pretty much looks like what we had early on. This normalizes it to 1. But now you're looking at z value of this. That would mean you're integrating everything from minus infinity up to z, and that would give you the probability of having a function of value less than or equal to z. Anything beyond z, that would be on the other side, 1 minus that. So that's what they call the standard normal cumulative distribution function. And that would be represented by this. That would be your curve that represents that function. You're integrating everywhere from minus infinity up to z. Now they just showed the z here. Z could have been over here, down here, anywhere there. And this would be the cumulative distribution of everything less than z. This would be the things greater than z, which would be 1 minus this. So once you have one of those, you have both of this. Again, this is where the mean of 0. And I think that standard deviation is probably 1. Looks like it. Okay, without numbers there, it's hard to tell. Okay. I don't think you really need to know the theorem, but if you ever do need, you can go back and refer to it. If x, sometimes that's called the expected value, or whatever, has a normal distribution with a mean mu, standard deviation sigma, then for all a's less than or equal to b, they're either a is less than b or up to and equal to b, the probability of your value, expected value being less than or equal to b, would be, boy, you have to read the book to find out what this capital F is, but it's b minus mu, how far off from the mean that was divided by your sigma. For all expected values left. So if the expected value was beyond b, this is going to be a number greater than 0.5, for instance. If you're trying to get the probability between a and b, your expected value between that, then you do the b would be this part, a subtracting off that part, and that would give you what's left in the middle. Hopefully they'll do a graph of that. I think they do. Yeah, okay. The capital F is the area under the curve, whatever that normal distribution. This one has a mean of mu, okay? And this one right here would have been everything here, minus this one, which is everything here. That then gives you the probability of your value being between a and b. Okay, enough of that. Again, if you need more, hang on to the book or find a book like it. You can get what you need there, hopefully. Let's now go to the part that you probably, wait, yuck, I did the wrong one, yuck. Get the talking and not paying attention. Go back here, sorry about that. I could have done it with an arrow. I didn't notice if the arrows were active. This sure is taking a long time. This is the part that you probably will, if you ever do much with this, you'll wind up here. Most, don't mean to be disheartening with it, but most applications you ever run into, you probably are never going to be able to find the exact fit for an integral, unless you're doing really simple stuff. If you're dealing with fairly complicated, why is this not opening? There it goes. I'll have to go through all this again. Just because I hit one button wrong. Okay, chapter 7. I think this is the last section. It's our 9, their 8, because they didn't do that section on summary of integration techniques or whatever it was called. But because most of the time in real life, if you're dealing with really complicated systems, those integrals are going to be, if they are integrable, they usually are so difficult to do you don't even want to try, but you wind up doing numerical integration, okay? All right. For instance, the ones we're just looking at, we said already, those are almost impossible integrals actually to calculate, except we use them all the time. We do them numerically. The areas under your bell curve are computed using numerical integration. You can't integrate that. You can't integrate e to the minus x squared over 2. It just, there's no substitution, there's no way to do it except numerical integration, okay? Estimating, okay? Using numerical integration. Now there's 3 rules I think we're going to look at. Yeah. And so sort of get used to these. The first of these is called the midpoint rule. Okay? And what we do here, I wish they showed the picture first and then the rule, but they're showing the rule first. Well, not quite the rule, but you know. You're trying to integrate some function that may be very difficult to integrate, may be impossible to integrate, but you can evaluate it. Any old function that's out there, usually you can at least evaluate it. You may not be able to integrate it, but evaluate it. So the function has to have a starting value, that'll be your x0 at a, and some xn, the last interval you're going to have is going to be at b. You're integrating between a and b. Now, you break that interval from a to b into, now notice, sometimes my enunciation isn't good. Don't confuse interval with interval. They're used similarly and together, but the interval is between A and B. And you break that interval into so many sections, okay? And generally that number is B minus A divided by N. If N is the number of sections, that's going to be your delta X then. How big is each section? The whole section is B minus A. You're dividing it into N pieces, so you have B minus A divided by N. And that'll be your delta X. So from the first one, you go over one delta X to get your X1, another delta X to get your X2, another delta X, X3, and on until you finally get to the last one, last delta X will be getting you up to X of N, which is B. If you have N of those sections. It's basically, I mean, almost like your old Riemann sums that you did in integration. We did, early on. It's basically going back to that, okay? So you could have these values anywhere in between, which is your alpha. Let's see. To me, these things don't say a lot unless you really are thinking about what it's talking about. Your jth value of y would be you go over starting at x equal a and do j delta x is past a, then whatever the value is there, that's your y sub j. That's your y sub j is alpha of x sub j. That would be alpha of a plus j times delta x. J is how many intervals over is that, and each interval is the delta x thickness. You started at a, so you add that to it. That would be your y value. And again, it's very similar to what we used to do with Riemann sums. So here's an example, okay? Now, they're starting with the trapezoid rule, not the midpoint rule, okay? In our text, we start with the midpoint rule, which I like to do a little bit better. So let's go over and see if we can find the midpoint. Here's the midpoint rule, okay? Why they changed these, I don't know. Why they ever did it in this way, I don't know. Okay, the midpoint rule, your nth midpoint approximation of the integral from a to b of f of x dx, you split do your b minus a, that's the total length you're doing, divided by whatever your n is. And m stands for midpoint, n stands for how many intervals you have. And your delta x is always b minus a divided by n, just like I was saying before. Okay? Now, for your midpoint rule, this x of 0 is a, x of 1 is the next value, x of 2, x of 3. We want that value in between these x's I just named. Okay? So you're going to do half a step beyond the first. So it's going to be a plus the jth midpoint would be go to the jth one, but step back half a step, and that's time your delta x. Okay? That's the midpoint between those. Is that really all that useful to remember that formula? No, in reality, you just see what the numbers are and pick them out. They're not that hard to do. But then your rule is you take the midpoint. Let's get a picture. I wish they did the pictures before they did. Here's the midpoint. Okay. Here's your x of a, here's your x of b. They've broken this into 1, 2, 3, 4, 5. Let's say n is equal to 5 here. Here's your 1. Your midpoint of 1 is going to be this value right here. So you go a plus your delta x over 2. Okay? That's going to be the value. That's where you calculate your functions. Okay. Now, when you look at this general function here, and you see you overshoot this much, undershoot that, undershoot a little, overshoot a little, undershoot some, overshoot some, undershoot some, overshoot a little bit, overshoot, yeah. So your midpoint, not going to give you exact, but it's going to give you reasonable, and that's your delta x. You sum up all these areas, and you say, how close is that to being under the curve? Well, how much were you over and undershooting? Okay? Now, I should have brought that up. Sorry, I forgot. This is a lot of blah, blah, blah before we actually do anything with it. They're saying that's also the sum of the areas of the tangential trapezoids. So we haven't talked about those yet, but that's saying if you take the trapezoid that you have, take that midpoint and do a tangential line at the midpoint, and a tangential line at that midpoint and this one, that's actually not a bad approximation. Not nearly as bad as this looked like here, because you're doing the upper curve basically of that. Okay? And that gives you a pretty good approximation. Looks like in this problem we overshot, awfully close on that one. Undershot, and undershot there too. So not a super bad. Now, where does that come from? Well, if you think what a trapezoid is doing for you, you take this height plus that height, in other words, take this trapezoid, flip it this way, that makes a rectangle, and then you have exactly half of the rectangle. And that's why that is a pretty good approximation of that. Because when you draw it that way, it looks a lot better. Okay, so let's go back to your form here. I guess we hit this well enough. That is how you actually do the calculations. Now, again, the actual doing of them is a lot easier than looking at these symbols. Okay, but that's what you use in the midpoint approximation. Okay. Now, that next slide, this one, is basically saying, I think, the same thing I was saying a little earlier. Now, this is how those two are equal, I'm sorry. The midpoint and the tangential trapezoid. The tangential trapezoid is the tangent line here, and right at the midpoint, there's your value of the midpoint. This part of the trapezoid and that part are awfully close to being the same. Okay, this includes the undershot of this. This is just about most of the overshot here, not quite all of it. And you see how the trapezoid would be the same area as this, because if you took that's your minor, that's your major, flip them like that, took the average, that would give you exactly half of that. So it's better to go from the actual area of the trapezoid, and then you see that exactly half of that is the area of your midpoint rule. Okay. For what that's worth. Okay. Now, the trapezoid rule, on the other hand, is not that trapezoid, but it's this one. And we need to go back, because the slide set is the reverse of that. Okay. All this was up the same here. But now, these values here, these give you the values at your boundary. You know, your A plus delta x, these are the values there. And if you use those values, you're defining a trapezoid, like here, okay? So here's your x of 0, which is your A value. X of 1 would be up here, x of 2 over here, x of 3 here, x of 4 here, x of 5 there. And if you do the lines here and here, in other words, just connected those values, then this is a trapezoid. The area of that trapezoid would be 1/2 the area of this plus that times this, because if you took this and flipped it over, you get a rectangle that would be this plus that. Pi delta x wide, and exactly half of that would be your trapezoid. Now, on first glance, that looks like that might be better than midpoint. In reality, it's not really quite as good, but it's pretty good. You undershot, right on the money here, overshot. Well, maybe this curve it would do just about as well. Okay, but again, not a bad rule. Okay, and again, a lot of blah blah blahs before we ever get to an example. Okay, and I think we're awfully close to getting there. Here is the I don't know if you'll find this helpful or not. The shaded trapezoid has an area of 1/2 the delta x times the sum of these two, the y sub j, x sub j plus 1, the y sub j plus 1 minus 1 plus the y sub j, the y value there. Y sub j would be this rectangle, y sub j minus 1 would be that rectangle. Add the two together and take half of it, you're getting half of the difference in between. There's one way to look at it. But if you remember how she did areas of trapezoids anyway, it's this line plus that line times this divided by 2, because like I said, take this and flip it over and around, so this line is over here, this line is over here, you get a rectangle exactly this plus this high, that wide, and that's exactly twice the area of what we're measuring here. So that's why the 1/2 delta x is in there. Okay. Average of the areas of the left and right hand rectangles. Okay. So here's the trapezoid rule. And this actually is a little bit simpler rule than the midpoint rule, just because you don't have the extra 1/2 in there. Your delta x is exactly the same. Your y sub j's are fairly similar, and it's just 1/2. And here's what you have to think of now. That first trapezoid was x0 to x1. So it would be 1/2 of the sum of those. And then the next one was x1 to x2. So you had two y1s in there. But then the next was y2 to y3. So you had two y2s in there. You had two of every one until you get to the last one. Then you only have one. So this is the trapezoid rule. And it's a pretty decent approximation. Not super great, but not bad. Okay? And finally, we get to example 1. Okay. I think this is it. Yeah. So let me actually, I don't even remember what color my pen is. Have I corrected that yet? No. Okay. Yeah. Calculate T8. Okay, that means trapezoid rule for 8 intervals. Okay? For the integral from 1 to 3 of sine of x squared dx. Okay? And it says then use a computer algebra system to calculate that for 50, 100, 500, 1,000, and 10,000. I think when you see the T8, you'll say, yeah, let some other system do it for the others, okay? We sure aren't going to do that in here. So how would we do this? Well, let's sort of plot it out a little bit here. I don't know if they actually draw it for you. I guess they don't. I was hoping they did. But you really don't need to see it anyway. What you're doing, you're going from 1 to 3. And that's not by scale, 1 to 3. You want 8 intervals, so there's 2, 4, 8 intervals. 1.25, 1.75, 2.25, and 2.75. Okay, there's your 8 intervals, equal intervals. Now I didn't do it the way probably you should have done. 3 minus 1 is 2, divided by 8 would be 4. 2 over 8 is 4, 1/4, you know, so that would be each interval is 1/4. So your delta x is 1/4. Okay? Now, for trapezoid rules, you're using those values. Okay? So this is going to be sine of 1. Right? That's going to be the y value here. This is going to be the sine of 1.25 squared. See, I could square 1. I can't do that one very easily. This will be the sine of 1.5 squared. This will be sine of 1.75 squared. Okay, so you got to do that for every one of them. Sine of 4. And be sure, by the way, In calculus, if you're ever doing a trig function, what are you doing in regard to? Which mode? Not degrees, radians. Always, always, when you're doing these, make sure your calculators, your whatever you're using, is doing radian modes. You don't want to ever assume degrees, because none of your calculus things work exactly for degrees. You have to have other factors in them. So be sure you're in radian modes. So this is one of the things you're going to do right off the bat. Sine of 2.25 squared. Sine of 2.5 squared. Sine of 2.75 squared. And sine of 9. Okay, you're going to do those values. Okay? And what's your rule then? The trapezoid rule would be 1/2, remember that's there, and your delta x is there, because that's your width of each interval. Okay? Then you do this one of those, plus 2 of those, plus 2 of every one of the others, you know, up to you get 2 of that next to the last one, and then plus just 1 of sine 9. That's 3 squared is 9. Okay? Now, I didn't write in all the stuff, but it's pretty easy to do. I mean, once you've got the things calculated, that's what you do. You just do 1 of the first one, and then 2 of all the others, except the last one, you just do 1 of those. Multiply all that by delta x and divide by 2. And that should give you your sum. So if someone wants to do it, let's try it real quickly. You want to do the sum first, or you want to, I'd say let's do the sum first. Because your delta x, you know, is 0.25, and half of that is 0.125. So we're going to multiply our final answer by 0.125. Just remember that. So if someone's got a calculator, sine of 1. Be sure you're in the radian mode. So sine of 1 plus 2 times sine of 1.25 squared. Now it's not sine squared, it's 1.25 squared. Take the sine of that. Plus 2 times sine of 1.5 squared. Okay, yeah. You do sine of 1 plus 2 times sine of 1.25 squared plus 2 times sine of 1.5 squared plus 2 times sine of 1.75 squared plus 2 times sine of 4.
Inside or outside?
The square is, you're squaring the number, not the sine function. Okay? Sine of those numbers squared. The number squared, not the sine squared. So 2 times every one of these squared, sine of every one of those squared, until you get to the last one, then it's only 1 of those, sine plus sine 9. Okay? And then, or do you get whatever you get that equal to, multiply it by 0.125, 1/2 of 0.25. And you should get an answer Does anyone get an answer yet? Well, you could divide by 8 or multiply by 0.125. I don't care. Yeah. 0.4, I think did you do 2 times sine 9 or only 1 times sine 9? Yeah. So subtract off of sine 9 from that before you divide it. The first one and the last one is just 1, and then the others are always 2 times. 0.4281. That's what the book got. Okay. Now, that's not a bad number, but they did it for n equal 50 rather than n equal 8, and then 100, then 500, then 1,000, then 10,000. And we got 0.42. 50 gave you 0.46. 100 gave you 0.463. 500, 4,632, 8, and then 1,000, 4,3629, 4,436,294. So you keep getting a little more precise, but you had to get an awful lot of them before you got to C. I don't know where it was, but by the time you got to 50, you had 2-digit significance. By the time you got to 100, you had 3 significant digits. By the time you got to 500, you had 4 significant digits. It appeared anyway. But this is one we can't come up with a good analytical answer. You just have to take his word for it. It looks like 0.4632 is about as close as you can get. Okay. Now, they never had us calculate one with the midpoint, which is sort of a shame. Next thing they go to is error bounds. Okay? Oh, here's what we did at the beginning. Now they're just showing you this. Earlier the figures are doing. This is your division into 8 equal subintervals. Okay? 3 minus 2 minus 1 is 2, divided by 8 would be 1/4, so every one of these subintervals is quarter thick. 1 to 1.25. All those are your intervals that you're dealing with. And each of those values is what you put into the sine function when you did the calculation. Okay. So, we've already talked about the midpoint rule, and let's just see which we think might be a little bit better. The trapezoid that we had, that we just did, was your it was either all in or all out trapezoid generally, I think. Maybe not. But the rather than sort of talk around it, we'll get to the comparison later. I was going to make a comparison between the two. Let's now talk about, oh, and by the way, in that sense, okay, the trapezoid, remember you had a factor of 1/2 before the delta x, okay? Then you had varying coefficients, 1, 2, 2, 2, 2, 2, 2, 1, okay? So you had to keep up with those. With the midpoint rule, it's just a delta x, not a delta x over 2. And it's just your values there, but they're the midpoint values, so the thing that's a little messier about it, for every interval you have to add half of an interval to that to get you the midpoint of the next one. So, give a little, take a little, you know. A little harder to calculate where to calculate from. Once you do, you don't have to keep up with 2s and 1s and halves and things like that. Okay. Okay. Seems like we've already seen that one. I'm trying to recall. I think we did, so let's move on from there. And there. Okay. I crammed down a bunch of bites of salad and wound up not drinking anything because I just ran out of time when the phone call and stuff happened. I need to take a brief pause and go get something to drink. My throat is just getting too dry. Y'all need a break, at least a stretch or something like that. I need to go get something to drink, so sorry. All right. Here are our error bounds for the trapezoid rule in the midpoint rule. Okay? You'll notice in your book it does midpoint first and trapezoid second. They're still the same. They have the numbers right. Okay? Now, here's an assumption. Whatever that function is you're integrating, okay? You're integrating function, right? To come up with the trapezoid rule, what you have to do is take not just the first derivative, the second derivative of that function, whatever it is. Now, usually we can take derivatives. If we can't integrate, well, that happens frequently, but you can usually take derivatives. So we take the first and then the second derivative of the function. Now, if that function exists, okay, now what that means is whatever your function is here, okay, your first derivative, of course, you expect that to exist everywhere. Your second, you hope it does too. Now, let me give you some examples of where it would. Like, first derivative wouldn't exist if your first tangent line is a vertical slope, or your last one, you know, or something like that. Those, if you run into situations like that, you can't do this. You know, it just won't work. But let's assume that, and most of the time, your second derivative does exist, and you want it to be continuous as well. So, what you do, you take the second derivative of the function that you're integrating, okay? And then you look at it throughout the spectrum, from A to B, okay? Now, a lot of times that second derivative is either going to be a max at the one end and a min at the other, or a min at one end and a max at the other. Sometimes it could go up and come back down. You just have to see what kind of function it is. If that second derivative turns out to be a parabola, it may be the max is somewhere in between, okay? What you do is take the absolute value, not just the value, the absolute value of that second derivative, and find the number bigger than that for the whole interval, okay? And that number, K2, is the reason for it being a 2, but we aren't giving it yet, okay? So your error for the trapezoid rule is that maximum value of the K2 anywhere on the second derivative anywhere on the interval, that K2 times B minus A, that's the length of your interval, Q. Okay, that could be a number. Depending on how long your interval is, that could be a pretty big number because you're cubing it. So then you divide it by 12 number of intervals n squared. Okay? That's your error for your trapezoid rule. Your midpoint rule, like we said before, is even better. In fact, it's twice as good. The K2 is the same, the B minus A to the third is the same, the N squared is the same, it's the 24 you're dividing by there as opposed to 12 here, so you got half the error in your midpoint rule that you did in your trapezoid rule. So midpoints are better, okay? Little bit harder to calculate, but not much. You just have to do a couple more steps at the beginning. Notice they didn't have us do a midpoint rule. Okay. Now, here is sort of a generalization type thing. Okay? And it sort of shows why that is the case. I want to say increasing functions, from here to here is increasing, but a curve that is concave up, okay? Curve that concave up. Your trapezoid error, which is going to be this point to that point, where your curve is like that, your trapezoid error is here. If you remember the midpoint error, it's sort of hard to see this way, but then when you did it this way, your midpoint error was here. Now notice, the trapezoid error overshoots the actual curve, the midpoint error undershoots it, okay? But the F double prime, when that is a larger number, the errors are larger, okay? Now look at when you're F double prime, this is a pretty large second derivative. This second derivative is pretty small. There's not a lot of concavity there. It's approaching a straight line there. So you see, for the same delta x here, okay, your area here is much less, okay? This area is much less. And again, you see your midpoint error is about half that of your trapezoid error. So if that F double prime is smaller, your errors are typically smaller. But you still have usually twice as much error on the trapezoid as you do on the midpoint. Okay. Now, with that in mind, do we have an example? Yes, example 2. Okay. This is one we can actually compare. My pen is getting tangled. Okay. All right. Here is what we're going to be estimating. Calculate M6 and T6 for the integral from 1 to 4 square root of x dx. Now you want to go on and actually do the calculation first, or you want to go on and do the M6 and T6 first? Second? Second?
We can go ahead and do the M.
Yeah, let's just do it. If I were doing the integral, guess what I'm going to write first? Yes, x to the 1/2 power, okay, dx, okay? And what does that integral become? X to the 3/2 power times 2/3, or divided by 3/2, which is times 2/3, evaluated from 1 to 4. And I think I can even do those calculations, okay? Because when x is equal to 4, I take the square root first. Square root of 4 is 2. 2 cubed is 8. 2 times 8 is 16, divided by 3, that would be 16/3, minus, and pretty easy to do with 1, that would just be 2/3. Right? And that would be 14/3. Okay? Make sure that, oh, they don't even do it, do they? Shame on them. Okay. 3 will go into 14. 4 point. Yeah. 4.666667. Okay. Well, let's do the midpoint rule. Thank you. Well, no, they've got it. They don't have this one right. Okay. Do they have it on a different page? No, that's right. That's the one. Okay. You're going from 1 to 4, and you're doing 6 intervals, so that's 3. So halfway in between is going to be your delta x. So your delta x is 0.5. 3 divided by 6 is 0.5. Okay, so this is correct. Okay, now for your midpoints, you don't just get the 1 and 1.5, 2, 2.5, 3, 3.5, and 4. For the midpoints, you got to get the midpoint in between those. So that's going to be the 1.25, 1.75, 2.25, 2.75, 3.25, and 3.75. Those are your midpoints. Okay, so your midpoint rule, remember, is just simply delta x times the function evaluated at those values. So what we do is do the square root of each of those and add them together. So if you got a calculator, square root of 1.25 plus the square root of 1.75 plus the square root of 2.25 plus the square root of 2.75 plus the square root of 3.25 plus the square root of 3.75. Total sum multiplied by 0.5. What you get? No, well, divide by 2 or multiply by 0.5. It doesn't matter. What you get? 4.66 what? 92. 4. Okay, they do 4.5. Okay, not bad. Okay, for the trapezoid rule, it's 1/2 your delta x. Okay. And on this, you use actually the endpoints, and I can do the first one. That would be 1 plus, because square root of 1 is 1, 2 times the square root of 1.5 plus 2 times the square root of 2 plus 2 times the square root of 2.5 plus 2 times the square root of 3 plus 2 times the square root of 3.5 plus 2. It's not 2 times, but just the square root of 4, which is 2. divide that one by 4, I think, because this is 1/2 times 1/2, which is 1/4. So multiply by 0.25 or divide by 4. Okay, let's get this a little bit. Okay, 4.6614 8. Did I give you one more digit? 8. Okay. Now notice here, just like we saw before, the midpoint. Okay, now here's the difference. The last one we saw was an increasing function. This is a decreasing function. Okay, so this time the midpoint is going to overshoot and the trapezoid is going to undershoot. But the midpoint is going to overshoot less than the trapezoid undershoots. Okay, in fact, it's twice as good. Okay. Now, okay, so that's what we've got here. Let's look at the error. We said calculate it, we've calculated it. Then it said calculate the error bounds. Okay, the error bounds for the midpoint, so E for the mid M6 would be, now remember how that goes? You've got in it your, can't remember which they did first. Oh yeah, K. All right, we got to do the K. Well, here's your function. F of x is equal to x to the 1/2. Even when I'm taking derivatives, I want to use this one. What's f prime of x? 1/2 x to the negative 1/2. And then your f double prime of x, negative 1/4 minus what? Minus 3/2, isn't it? Right. Okay? Now, forget about the minus sign. Okay? This minus sign anyway. Okay? I hope you realize that x to the 1/2 is a function, is basically half a parabola lying on the side, right? So your greatest curvature is going to be down here at this end. So your f double prime is going to be closer to 1. So let's plug in a 1 there. 1 to the, that's going to be 1/4. Okay? Now if we plugged in the 4 there, you would have square root of 4 is 2, that would be 8, so that would be 1/8, that would be 1/32. Forget about the plus minus because I think it has to be back. Okay? Forget about the minus. So basically 1/4 is going to be your max. So that's your K2 is 0.25, right? Isn't that what I just said? Yeah. Okay. Now, B minus A, that's 3, right? Raised to the 3rd power. 27, that's a pretty good sized number. Okay? Divided by, and this is midpoint, which is 24 times 6 squared, isn't it? Yeah. Okay, n is 6. Now, let's see what we get here. This will be 0.25 times 27 divided by 24 times 36. Okay, I know this will go 3, 4. This will be an 8 here. So 0.25 divided by 32. Pretty small number. What you get? I hope I did it right. 0.25 divided by 32. Say again.
0.0078.
Okay, blah, 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 blah. Okay. Ooh. All right. Now, do the error for the trapezoid, and you just double that. 0.0156 or something like that. Okay? Because it's same thing, but you're dividing by 12 rather than 24. All the rest of the numbers are the same. And sure enough, we know the answer is 14/3, which is 4 2/3, 0.6667, whatever. Okay? Well, your midpoint rule said you were guaranteed to be within, boy, I wrote these in weird places, 0.007. We're even closer than that. We're 0.003 or less. Okay? And the trapezoid rule said you were within 0.015. We were actually between 0.005. So we were within that. Okay? So, sure enough, we were a little bit closer on the midpoint rule, overshooting, undershot the trapezoid by about twice that. Okay. Now, oh, they did the interval exactly too. I didn't see. Still don't see where they. Oh, there's the answer. 14/3. So we did it first. They did it second. Sorry about that. So they got 0.0078. Sure did, and 0.00156. Same thing we got, and the exact value of 14/3, which is 4.6667. Okay. Now, quite often we do it the other way. I mean, yeah, you can estimate the value, but and a lot of times what we want to do is, before the fact, sort of see if how close we can get. Okay? And this would be example 3, obtaining the desired accuracy. What we're looking for is find the n for a Tn, that's a trapezoid approximation of the integral of 0 to 3 e to the minus x squared dx. Okay. Guess what, team? Can't do that integral, so we can't test it for sure. But we want an error of at most 10 to the minus 4. So the error we want to be less than or equal to 10 to the minus 4. Okay? Well, what is our error for the trapezoid rule? That was your K2. Now we can calculate K2, right? If this is your function, f of x is equal to e to the minus x squared, what is f prime of x? E to the minus x squared negative 2x, right? What is your f double prime? A little messier, but still doable. What we got to do here? Huh? Okay, negative 2x e to the minus x squared times another, that'd be 4x squared. Okay? That's ugly. I was trying to save some writing. I think I'm going to lose. I lost way too much. Okay. That's just part of it. Plus, or it may be a minus. Okay. I think that will be a minus. Say that again. E to the minus x squared. So again?
2.
2? Okay. I believe that's a minus there, isn't it? Yeah. Okay. Yeah. Okay. Now, what we got to figure out is, what is this function doing? Well, this is an exponential function, negative, okay, so it's going basically like this, okay, pretty sure it's going like that. So you anticipate your greatest second derivative is going to be on the small end, but let's just evaluate it at both ends. Okay, at 0, that's going to be a 0, and this, forget about the sign here, this is going to be 2, right? So that would be a 0. So at the small end, we've got less than or equal to 2, and at the bigger end, that would be 4 times 9 times e to the minus 9 minus 2 times e to the minus 9. Might be better to do this as e to the minus x squared times 4x squared minus 2. That might be a little easier. So if you got a calculator, do this one. E to the minus 9 times 36 minus 2 is 34. Yeah.
0.0041.
Wow. Okay. I would say it's bigger at the upper end. So we'll use a 2 there. Okay. So the error is 2. The interval is 3. 3 cubed is 27. Divided by 12. This is trapezoid rule. And your n is n of 6. And 6 squared is, oh, what was it? Am I right? No, oh, that's what we're looking for. I'm sorry. N squared. Okay? We want that to be less than or equal to 10 to the minus 4th. Okay? So what we got to do is multiply both sides by 12. So that'll be 12 times 10 to the minus 4th. Divide both sides by, well, let's see. Clean that up a little bit. It's messy. Terribly messy. Okay, let's go on and make this a 6 here. Divide this and make it a 6. So make that 6 times 10 to the minus 4th divided by 27. Okay? I did this really poorly. Forget that. Let me start over. Okay. Okay. I hope I get all the numbers back in where they were. That was a 2, and that was an n. Okay. Let's multiply both sides by n squared. Okay. And divide both sides. Let's go on and get this to be a 6. And divide everything by 10 to the minus 4. So it's 27 over 6 times 10 to the minus 4. Okay? You can fiddle around with numbers there, but do what that is. 27 divided by 6 times 10 to the minus 4. Yeah, and then you'll take the square root. 212 points. So let's say 213. Always overshoot a little bit, even though your error is already done. So let's see, what did they get? They said 212.1. I'd like to see them do 212.1 intervals. No, I wouldn't. That's a mess. I'd say 213 intervals. Okay. Oh, there they did conclude that T213 would have an error of at most 10 to the minus 4. Okay. And they actually showed the graph of your F double prime there, and they got the same thing we did. And they did show it was greater at the left end, x equals 0, much greater than it was at x equals 3. Now, it did have a hump in between, but it wasn't a big enough hump to overcover that. All right, well, guess what? There's a better rule than either one of those, and that's Simpson's rule. Oh, sorry about that. Why this figure is here, we already finished that problem. There's the one we did before, and your greatest second derivative would be at the lower end of that one, also at 1. Okay, and there's your second derivative of this one. Now this one almost was enough to make me miss it, because I just assumed it was one end or another. There really was a curvature here too. Second derivative increased it here too, but it didn't go high enough. So it was at the ends of this one, so you should have been comparing this to that, but still not very obvious that that would have been the case. Okay? I think it is obvious the greatest curvature was at the very beginning. Okay, now, this is leading toward Simpson's rule. Now, I don't see this particular figure in the text, but one fairly similar to it is figure 12. It's figure 11 in the text. And here's what Simpson's rule does. Oh, no, I'm sorry. This is your concavity. Sorry about that. Yeah, and this is something I had already pointed out too, that when you are concave down, your trapezoid rule undershoots and your midpoint rule overshoots. When you're concave up, it's the opposite of that. So we already pointed that out on the increasing function, or on the concave up function. We just hadn't shown that here, but I'd already said it. So nothing too new there. Okay. Now, Simpson's rule. This is one way to do it. Do the tangent rule for n over 2 and the midpoint rule for n over 2, and the 1/3 of your total of your tangent rule plus 2/3 of the total of the midpoint rule, and that'll give you Simpson's rule for the n. Frankly, that sounds like a lot of work, and it is a fair amount of work. They don't come right out and say why that's the case, but it is the case. And we saw, I mean, if we just looked at it, one increasing function or decreasing function, one of these overshoots, one undershoots. So some combination of the two, but we knew that the midpoint rule is twice as accurate as the tangent rule. So give that double weighting, this half weighting, and you should come up with a much better approximation. That's what Simpson's rule is. Now, is that how we got Simpson's rule? Okay? Not quite, but, well, it depends which is the chicken and which is the egg. Back when I took calculus, my professor actually did it the other way and then showed us this was it. They're doing it the opposite way here. They're saying this is what it is, and then they'll show you the other. Now, trying to see where this, you can see this as a figure here. Okay. I don't see that showing up here. I know what they're talking about, but I don't see it here, so let's just skip it for now. Here is figure 12, figure 12, which is our figure 13. And this is example 4. I wish I'd have given the rule first. Let me go on and do the rule. Here's Simpson's rule. Now this is not doing it the way they first said. Do all of the trapezoid rule, do 1/3 of it, and then do all the midpoint rule and do 2/3 of it, and add them of the half values and then add them together. Boy, what a pain. Here's what Simpson's rule. Now Simpson's rule requires that the n be even. Doesn't matter what even number it is, it just can't be an odd number. Remember, midpoint trapezoid, you could have 5, 3, 7, whatever. Now you have to have an even number. Okay. So then the nth approximation to this function would be, now remember midpoint, no, trapezoid rule had a coefficient of 1/2. Midpoint rule didn't have a coefficient here, it just had delta x. This is 1/3 delta x. That's one difference. Here's what the rest of it is. Okay? It's kind of like, well, if you think about it, if you had written out what the midpoint rule was in the trapezoid rule, remember Simpson's rule was 1/3 of trapezoid, 2/3 of midpoint. And then you use those coefficients and dealt with them, you come out with these. But here's what we got. Use this one once. Remember that we only used it once before. 4 of these, 2 of these, 4 of these, 2 of these, 4, 4, 2, 4, 2, 4, 2. But then the last one, next to the last has to be a 4, and that has to be a 1 again. Okay. Where the delta x is defined just like it was before, and your y values are just like they were for the easy trapezoid rule. You didn't have any of the 1/2s there. Okay. So basically you've doubled everything so that you are using the 1/2 bit. So here is kind of the better way to look at it. Both the midpoint and trapezoid rules are kind of like doing linear approximations. Because one was a trapezoid between at the midpoint values, the secant between these two values, and the other was on the tangent of that. Okay, so they're both sort of linear approximations. What your Simpson's rule is kind of a quadratic approximation between every 3 points. And that's what they showed in our book, but didn't show on the slide set, is that for any curve, you can approximate it using a parabola. And you come up with a pretty good approximation, okay? But you're weighting things differently, and the other way of looking at it is your values and stuff. But just remember this for this one, for the Simpson's rule. It's a 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Okay? Always next to the last one's a 4 for this. Okay? And that's one of the reasons you have to have an even number so it works out that way. Because if you notice, you've got an odd number of terms there because you've got field odds. So you got 1, 2, 3, 4, 5, 6, 7. Okay? And subtract that from 1. It has to be an even number. So that's the rule. Now let's back off and do the problem. This was example 4, I think it was. Yeah. Okay. use Simpson's rule with n equal 8, that's perfectly fine, to approximate the integral from 2 to 4, square root of 1 plus x cubed dx. Okay. Try like you might, you're not going to find an exact value for that one, I don't think. I can't see that anywhere. Okay? So, one of the first things we've got to do is find what our delta x is. Anyone tell me what that is? And we're doing s sub 8. Okay, it would be 4 minus 2 is 2 divided by 8 is 1/4. So 0.25 or however you want to name it. Okay? So, now that I look at this, I don't think that has anything to do with our problem here. Let me see if we got a better one. Here it is. This is it. Sorry. So let me rewrite this. The integral from 2 to 4 of the square root of 1 plus x cubed dx. Okay. And like you said, 0.25 or 1/4. And you're starting at 2 and going to 4. So you got 1, 2, 3, 4, 5, 6, 7, 8. Okay. So those are your values. Okay. Now, I kind of like the way they do it here. I think I'll blow this up so you can see this a little bit better. When I have to write, I have to bring it back down again. Notice they wrote your endpoint, 2 to 4, 8 intervals, 1.25, 2.5, 2.7, all like this. And then they put the multipliers, the weighters above the top. 1, 4, 2, 4, 2, 4, 2, 4, 1. Okay? Put those above it. And then you're going to do your calculations based on these values with those coefficients. Okay? So, what this is going to be is 1/3 of 1/4, that's your delta x, times. Okay? Plug in a 2 there, and you have the square root of 9, which is 3, with a multiplier of 1. Okay? Plus 4 times the square root of 1 plus 2.25 cubed. Okay? Sorry about that. Okay? Plus 2 times the square root of 1 plus 2.5 cubed. Plus 4 times the square root of 1 plus 2.75 cubed. Plus 2 times the square root of 1 plus, I'm sorry, 1 plus 3 cubed, which would be 27. I can do that one. No, I'm off one. No, that's right, that's right. Plus 4 times the square root of 1 plus 3.25 cubed, plus 2 times the square root of 1 plus 3.5 cubed, plus 4 times the square root of 1 plus 3.75 cubed, plus the square root of 1 plus 16. So that would be square root of 17. Okay? That's a lot of punching on the calculator. Thank you for giving us such a miserable problem, but we can do it. It's just as a pain in the neck. What you have to do is remember to get your coefficients in there in the right place and plug in the values. But you got it. And then when you get to the end, add all those together, you can either divide by 12. In fact, dividing by 12 would be the easy way to do it. Try and multiply by 1/12. Dividing by 12 is much easier. 10.39. Let's see how they did. They got 10.74. So you're pretty close. 10.74159 is what they got. Okay? It's easy to not plugged in the number quite right.
Mine's 10.3974.
Second?
Mine's 10.3974.
Okay, I may have said something wrong. I think I did. I'm sure I did. This is not 16. That should be 4 cubed. Right? Yeah, 4 cubed is 64. So I'm sorry. That's where I messed up. It's 1 point. That should be the square root of 65. Okay. Sorry. I messed that up. You probably punched it in the way I said to.
I just thought we would put the number that said before.
That's what, yeah, I know. But yeah, that's happenstance, I think. Okay. Now, that gives you Simpson's rule. So far, we haven't seen how good it is. We figure it's going to be better, but we haven't seen. It says the accuracy of Simpson's rule is impressive. Using a computer algebra system, we find that approximation of example 4 is an error of less than 3 times 10 to the minus 6, and that was just 8 intervals. Before, we were having to go to 50 or 100 intervals to get that kind of approximation. All right, example 5 then. Let's see if they got this in here. I think this is it. Yeah. Here's example 5. Okay. The velocity in kilometers per hour of a Piper Cub aircraft traveling due west is recorded every minute during the first 10 minutes after takeoff. It says use Simpson's rule to estimate the distance traveled. Okay? Now, in this case, we don't have a formula, we don't have an equation, we don't have an integral, but basically what we're doing is integrating, because if you integrate d of t dt, then, well, got a little bit of adjustment to do here, but if you integrate that, you should get a distance, because distance is equal to velocity times time. The problem is this is kilometers per hour and that's minutes, so you got to do an adjustment here. Probably easier to divide this by 60. And that would give you what fraction of an hour that would be. Yeah, and they do that. Okay. So the distance traveled is the integral of the velocity from, we convert minutes to hours because, okay, where did they convert their minutes to hours? I'm not seeing that. Yeah. But, I mean, basically, your delta t, which is what you're doing, that's 1 minute, which is a 60th of an hour, that's where you do your conversions. That's the only place you have to do it. So by Simpson's rule, this would be, remember Simpson's rule, oh, I got to do back. And remember your coefficients, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. That last, next to last always has to be a 4. Okay? Your intervals are not in minutes, but 60th of an hour, so that's where that comes in. So Simpson's rule for, what do we call this, 10? Yeah. Would be 1/3, and we, doesn't matter what that is, 1/60th, because that's your interval. And then here's your sums. I'll do the first one, 0, okay? 4 times 80 plus 200, because it's 2 times 100, plus 4 times 128, plus 2 times 144, I could have done that one in my head, plus 4 times 160, could have done that one in my head, plus 2 times 152, plus 4 times 136, plus 2 times 128, goodness gracious, plus 4 times, don't you like doing these, 120, plus 160, I mean 136, okay. Much easier to do this time than all the others, except getting the numbers punched in right. It would be 320 plus 200 would be 520 plus 4 times 128 plus 288 plus 640 plus 304 plus 4 times 136 plus 256 plus 480 plus 136. 20.44. They got 21.2. I don't know. I may have written something wrong. Or I could have punched something wrong. Yeah, but anyway, they got 21.2. You got 24. So it's not far off. All right. Afraid we're at the end of time, aren't we?
Yeah, 140.
What's that?
It's 140.
140. Okay. So we didn't quite finish. Boo hiss. Once upon a time I had, oh, there it is. All right. We'll talk about the error bound next time. And I mean, that close to finishing. Oh, here we go. Wow. We did cover some ground today, though. And we're right at the end of the chapter. Now, in reality, these are 3 ways to estimate integration. In real reality, basically, you do, like I was saying before, your Riemann sum type thing. You just do delta x. You actually do that kind of stuff, and you go back to doing sums. And if it's not precise enough, you take out. These certainly work, and they're fine, and we'll talk about the rest of it. But we are through with. When we finish this, we'll be through with chapter 7. Now, where do we go from here? Okay? Sort of want to remind you. Chapter 8, we're just going to look at a couple of things. 8.1, 8.2, and probably 8.3. Okay? Chapter 9, Introduction to Differential Equations. You're going to do a course in that sometime later, probably, right? Not going to do that. Okay? Chapter 10, Infinite Series, we're going to do 10.1 and 10.2 only. Chapter 11, Parametric Equations, Polar Coordinates, and Conic Sections, we'll just do 11.1 and 11.2. So when we do those sections, 8.1, 8.2, 8.3, 10.1, 10.2, 11.1, 11.2. There'll be a test on those, let's see, 7 sections, just that. So it won't be a chapter test, it'll be a unit test kind of. And then if we have time, we'll get into vector geometry. Should have gotten there, but I think most of you are probably already somewhat familiar with that, but we'll do. So that's where we'll pick up and go next time. We basically lost 2 weeks out of our 10 this summer with all the mess that I had to do. So let me give you your test on this chapter, chapter 7. Can't remember if I have all of the first test in. Maybe not quite. There's one more. Well, I had some made up already. They're in a different place. Let me find that. Test 1. Oh, and Khalil West without getting one. Yeah. I meant to tell everybody not to leave until you got a test. I told my first class that, but I forgot to tell this people. Okay, someone read to me the first question. I have 2 different test 2s in here. I don't want to give you the wrong one.
Integral from 2 to 4 of log of...
Wait. Evaluate the integral, is that right?
Yes.
And it's integral from 2 to 4 log blah, blah, blah?
Correct.
Okay.
At least I didn't miss the day it was handed out.
What's that?
At least I didn't miss the day it was handed out.
Yeah.
That schedule worked out.
Yeah. All right, good deal. Finished. Good deal. Thanks. All right, we will go from there. Have a good weekend. Guess what? We'll have 2 classes a week from now on. I hope. Did any of the rest of you